So we take the first worksheet and we flip it over 13 times, 9 times, 1 time, and we get to question 2. So very similar question that we just completed for number 1 if you were with me for that video. Now we're going on to number 2. Now this is a little bit more difficult because we have some different stoichiometric ratios that pop up. Okay, so let's get started. We have a white precipitating formed when we have a solution of potassium phosphate. So that's our chemical name, potassium phosphate. And that phosphate is a polyatomic ion. So that kind of gives it away. If it was phosphide, IDE, I knew it would be just phosphorus. And then we have calcium chloride. So again, just working our names, calcium chloride. Now that IDE ending gives it away, that's binary. All right. And what we know is the positive ions go in front, the negative ions are in the back. And this is an example of another double replacement reaction, metathesis reaction, or it's also a non, of course, redox reaction because the ions are staying the same. So this positive potassium is going to go with the negative chloride. So we'll have potassium chloride. We're just going to switch partners, do-si-do, if you're into, again, square dancing. All right, I don't know how many people are. Calcium phosphate, right? This calcium is now going to switch partners and the positive ion goes in front. So the calcium phosphate. All right, you're done. Now we have our chemical formulas. As we said before, potassium is a group 1 ion, so it's K+. Phosphate, okay, we can look that on our table, and or you should know, maybe, depending on what kind of course you have, is PO4, and it's -3. This whole thing is -3, yeah, and K is +1. So to balance this off, you're going to need 3 potassiums to get a total charge of +3 to balance off the -3 to give you a neutral compound. That's the whole point of writing chemical formulas, is to write a neutral compound. So that's K3PO4 is potassium phosphate. Now, as I said before, that chloride ending tells me I just have chlorine, and I have calcium. Now, calcium is a group 2 element. It's an alkaline earth. It likes to become +2. Chlorine is a halogen. They're -1. So if this guy is -1, this is +2, you can guess you need 2 of these to make that a neutral compound. And as we said before, we're going to switch partners. This positive is going to hook up with this negative to make potassium chloride. K is +1 for reasons we just explained. And chlorine is -1. So that's a 1-to-1 nicey. All right. And now we have... I don't know why I'm switching colors, but I'm just going to go crazy here. Now I have potassium and chlorine. How about calcium and phosphate? Calcium is +2. Phosphate is -3. So one technique to figure this out, if this is -3 and this is +2, as you may remember, you can do the crisscross method. There needs to be 3 of these calciums and 2 of these phosphates. Now to show 2 phosphates, you would need some parentheses. And that's how we would go about doing that. Okay, so back to reality, up there goes gravity. Now we have to balance, because if we're going to use these relationships, or we're going to use these mole relationships, that's what stoichiometry is, we have to make sure we have the right number of coefficients numbers in front. And again, when you balance these type of ionization reactions, I like to keep the polyatomic ions together. It makes my life easy. So I see I have 2 phosphates here. I have 1 phosphate polyatomic ion. I'm going to throw it 2 here. This gives me 2 times 3, 6 potassiums. So I put 6 here. I balance my potassiums. That gives me 6 chlorines. I have 2 here, and I put a 3 in front. And notice the only thing I'm doing by balancing is putting the stoichiometric coefficients in front. I'm not forcing the chemical formula to change here. 3 calciums, and now I'm balanced. Don't forget, nothing in front implies a 1. You don't have to write it, but there it is. So we've balanced our formula. Now we're ready to do the work here. And the work very simply is they're trying to find, just like the other worksheet, the limiting reagent, okay, and the excess chemical. From 2 what? From 2 solutions. So before we do so, let's try to eliminate some errors by looking at the net ion reaction and kind of getting rid of thinking about the spectators, at least initially. So what I like to think about is in these types of reactions, and this is what really is going to be asked of you, okay, on a test, not so much these guys, but this gives you the overall. And so what's happening? Well, we have to identify our precipitate before we can actually know what is actually happening. If there is a precipitate, if there isn't a precipitate, there's no reaction. So we go to our solubility rules, or if you have a worksheet that'll help you with that, or a table. We know group 1 ions are always soluble, so boom, this is aqueous. We know that halogens are soluble. They're -1. They have a low charge, just like a +1 has a low charge, so the Coulombic attractions in the crystal are weak. And there are some exceptions to chlorines, and that's lead, mercury, okay, and silver ions, and calcium is not one of those exceptions, so we know that it's aqueous. And what does that mean? That means I have two containers that have free potassium, free phosphate, free calcium, and free chloride ions. And then we pour them together, okay, well, maybe there's a precipitate. Let's see. Well, group 1 ion, potassium, and a halogen for 2 rules and 2 reasons we just explained, this has to be aqueous, meaning they're free ions. Now, for calcium, who's +2, and phosphate, who's -3, as I tell my students, if the charges are generally above 1 and 1, in this case, +2 and -3, you can almost always assume that they're going to be a precipitate and a solid. In this case, it's true. It doesn't almost always work. There are some exceptions to that, but almost always if you have a high charge, and again, Coulomb's law is F is equal to some constant times R1, which is the charge, let's say, of the positive ion, R2, the charge of the negative ion, over the distance squared. So if the charges of the positive are high and the negative are high, that's going to increase my force of attraction between the crystal, and that water cannot compete to separate them and dissolve them, so they stay a solid. So the high charge ions find each other, or at least they collide with each other when you pour these together and make a crystal structure. And that's the precipitate, the solid that comes out. So what's the overall picture here? What's the overall reaction? Well, we took a calcium and we took a phosphate, and they came together and they made calcium phosphate. And you can see this is Ca3 and it's PO4, 2. So I need 3 calcium +2s to 2 phosphates. And you can already see from the first side that this is a little more challenging in terms of the different ratios, but very easily done and taken care of. So of course the precipitate, all right, is right here. It's the solid. And again, it's based on solubility rules. It's also really based on Coulombic attractions. And you can break it down to large positives, large negatives, essentially will attract each other strongly than the water to break them apart. But this is the overall reaction. I'm eliminating what? All the spectators. Okay, so this is a limiting reaction problem. And I also almost always suggest to use the mole table to do that. Now, if you don't like to and you want to do this longhand, you can do this stoichiometrically longhand. But I'm going to go through an easier method. Sometimes I think that eliminates most errors in this process and actually makes it quicker. So I have my ice table, initial, change, and at the end of the reaction. And I need my initial concentrations. I should realize that there's no precipitate in the beginning, because we're pouring 2 solutions that are soluble, okay, in the beginning. And when I pour them together, only then can the ions that are highly charged find themselves. So that's going to be 0. What's the initial concentration? Well, I have to go back into the problem, and we have to find some information here. Okay, so when we go back into the problem, we're going to see that for calcium chloride, we have a volume and a molarity. And we're going to multiply them together to get the moles. So let's clear out some space above here. I don't think we need a title or any of that there. So let's do that. And so for calcium chloride, or really the calcium ions, right? So remember, there's 1 calcium ion per the formula, so that will be the same. So for the calcium ions, I have 3.0 times 10 to the 2 milliliters. So that's going to be 300 milliliters. Now, remember, I have to get rid of liters when I multiply by molarity. So I'm going to times this by 10 to the negative 3 and see what does that mean? What am I doing here? By timesing to the negative 3, I'm essentially converting this to liters, right? If you think about it, if I have 300 milliliters and I want to convert this to liters, milliliters would go in the bottom, right? And you would go, for every 1 liter, there's 1,000 milliliters, and that's how you would do it. Well, 1 over 1,000 is 10 to the negative 3. So I guess I really should have my unit here. So let's do this. So 10 to the negative 3, that's why I do that. 1 over 1,000 is 10 to the negative 3, and I guess I should put liter over milliliter. Okay, and of course that gives me liters, and then I'm going to times that by my molarity, which is 0.250 moles over the liter. And we're going to cancel little hearts away, just like that is. Remember, this right here is really that. Liters go bye-bye, and I'm left with moles. So you put that in your calculator, and you get 0.075. And that's, of course, moles of your calcium plus 2 ion. Again, careful, careful. There happens to be 1 calcium per one of these formulas, so that works out very well. Okay? So the next piece is we've got to find our phosphate ion in our what? Value here. So same idea. Okay? So my phosphate ion, PO4, negative 3. And same idea, they gave me, in this case, 2.0 times 10 to the 2 milliliters, so they give me 200 milliliters. I'm going to times it by 10 to the negative 3 liters per milliliter. Milliliters go bye-bye, that gives me liters, and I times it by my molarity, which is 0.200 moles per liter, and you can see we get moles. So we put that in our calculator, and we get 0.040 moles. Now careful, careful, careful. Just so happens to be 1 phosphate per one of these formulas. So therefore it equals the same. But if there were 2 phosphates, I'd have to multiply by that too. So careful about that. Just don't always assume I just take it and find the moles. I've got to look at my ratios. That's what stoichiometry is constantly about, the ratio of how many. So the initial calcium plus 2 is 0.075 moles. And this is 0.040 moles. Okay? And now we're going to go on and do our stoichiometry. Now, what makes this a little challenging is that we don't have this one-to-one like the other side. So we're going to, again, the whole purpose of this is to find a limiting reagent. So how do we go? Well, if I want to see how much calcium ions in moles, these are all moles in the table, is needed to make all of this disappear, all right, I see there's a bigger number. I need 3 over 2, so I have times my value by 3 over 2, okay? So which is the same thing as times it by 1.5. So again, to take my moles, and if all of this was going to react, okay, I would need 1.5 times this value, at least that, to make this all disappear and limit the reaction. So I take 0.40 and I times it by 3, divide by 2, or times it by 1.5. It's the same thing. And when I do that, I get 0.06. Whoa! What does that mean? I'm going to write that down. 0.06. I'll put 0 here. What did that mean? Well, when I did that, I can see, party people, that I have at least 0.06. In fact, I have more than enough. So I have enough what? Calcium plus 2 to make all of my PO4 go bye-bye. So I know this is going to be minus 0.040. I know this is going to go to 0. I found my limiting reagent because I noticed that I have enough calcium to make all of this disappear. Now, how much of the calcium disappear? Well, 1.5 times this value, which is 0.06. So that much disappears. And at the end of this day, you subtract 0.06 from 0.075, and you get this remaining excess. Okay, so clearly our limiting reagent from doing this analysis, okay, is the phosphate ion, PO4 -3. You could also say K3 potassium phosphate is also, okay, our limiting reagent. Either one I would accept. All right, now what's happening to my precipitate? Well, what's the ratio? This is a 1 in front. So if this is totally being used up, 0.04, hey, this is a 1 ratio, so this would be a 2 to 1. So again, think of ratios. So to go to here, this is 1 is half of 2, so you'd be timesing 0.5 or cutting in half. So clearly, party people, I'm going to put a plus because we're going to make the product, and this is going to be plus 0.020. Come on, that's easy. And if you really want to have some fun, this is crazy, you can share this with your family. Look at this. This is a 3 to 1. We're going to lose 0.06 and 3 to 1. So what's a third of 0.06? 0.02. Hey, makes some sense. We'll add that to 0, put that in your calculator, and I'll wait. Obviously, it's 0.020 is how much moles of the what? Precipitate I'd make. Okay, so there you go. Excellent. So that's how we do this. So B, excess reactant. Well, the reactant is going to be my calcium. Clearly, the excess chemical is my calcium plus 2. Now, what do we know? Well, we know that there is 0.015 moles of it remaining. And we want the final concentration. Don't forget, party people, we poured these two solutions together. That's the worst arrow I've ever drawn. That looks like more like some kind of animal, but that was supposed to be an arrow. Okay. So these things make a big arrow. You're going to pour these guys together, and there we go. So we're pouring these guys together. So 300 plus 200 gives me a total of 500 milliliters, right? I'm going to add these two solutions. We're assuming that the volumes are additive, okay? And in any case, you add them together, you get 500 milliliters, which is essentially 0.5 liters. So we're going to put that in the bottom. So the total new volume is 0.5 liters. And we do the math. This 0.5 doubles everything, so 0.030. And I'm going to keep how many sig figs in my questions? I'm starting you guys with 3 across the board. And the bird. Okay, bird is the word. So I have, remember, leading zeros don't count, so that becomes my concentration, my molarity. Okay, so the excess is, so the calcium, all right, the excess calcium concentration is equal to 0.0300, or you can just say 0.3000 m. Remember, leading zeros never count and ending zeros do. That's why we have 3 sig figs. Okay, as we're moving forward here, how many dissolved calcium ions will be produced in the reaction? How many calcium ions? So I guess I never really asked about how many grams of the precipitate, so we really didn't need any of this, but hey, that was a lot of fun anyway. Why not do that? So how many dissolved calcium ions? Well, I do know that I have what? 0.015 moles. Careful what I'm asking for here. How many? Mole is a how many variable, but it's kind of a condensed one, right? It makes it manageable. What does a mole actually represent in terms of the exact number? And that's Avogadro's number. So for every 1 mole, we have 6.02 times 10 to the 23. And that's number of stuff. In this case, it's ions. So that's all I'm doing. And of course, when I do that, I get 9.03 times 10 to the 21. And that's calcium plus 2 ions. All right. Last little piece is our drawing. Okay. Now we have a precipitate. So getting artsy again. Our precipitate from our math and our solubility rules and our equation is calcium phosphate. Now, I don't expect you to know what the structure is of this, but Generally speaking, here's my calcium plus 2. It's attracted to the phosphate PO4, -3, to another phosphate, -3, and this would go to, let's say, a calcium plus 2. Again, I'll just leave it at that. Yes, it's because of the +2, -3. That's not the actual ratio or the actual how it reacts, but we'll just leave it for that to make this a simplistic type of relationship. Obviously, there's going to be 2 calciums, so let's just draw the second calcium for fun. Okay, so we have some kind of relationship here. Now, what am I going to do? Well, I do know, let's go find our limiting reagent. Let's go find our spectators who didn't react at all. Okay, well, we eliminated the what? The potassium. All the phosphate was what? Taken up. There's no extra phosphate. All the phosphate's gone. And the phosphate came from where? Potassium phosphate. All right, so for every 2 phosphates, okay, how many potassiums would I make? Every phosphate here, there's 3, but every 2 phosphates. And in my drawing, I have the 2 phosphates, what? In my salt. So the 2 phosphates in my salt, okay, then I should have 6. All right, look at that. For every 1 phosphate, or 2 phosphates, every 2 phosphates, we have 6 potassiums. And the potassium ions are aqueous. They didn't get locked up. I should draw 6 potassiums. So I'm going to do that and have fun doing so. K plus, K plus, K plus. I'm using this model that's representative of the ratios. 1, 2, 3, 4, 5, 6 to the 2 phosphates. Okay, where are my other ones? Well, chlorides. The calciums, okay, or the chlorines came from the calciums. Now we know something, we used up some of the calciums. That's important to realize, but we do know that most of the calciums, let's just start with the calciums that are locked up, okay? So let's start that way. We know that there's some calciums locked up. There's 3 of them in my drawing, okay? So for every 3 calciums, how many chlorines do I have? Well, for every one calcium, there's 6 chlorines, right? Every one of these, there's 2. So if there's 3 calciums, then there's 6 chlorines. See, it's right there in the balance formula. In every 1 calcium, there's 2, but there's 3 calcium, 3 times 2, 6 chloride ions. So for the 3 calciums that I have in my crystal, okay, I'm going to draw how many chlorines? 6. Let's put them in there. And I'll just put them randomly. Now, these chlorines that I'm putting in here represent the chlorines that match this stoichiometric ratio with these calciums. But we have to think a little deeper now, because if you think about this, some of the what? Calcium was used up. Some of the calcium chloride. See, the calcium chloride is your excess chemical. That means there's going to be some extra chlorines and extra calciums that are not all locked up. So let's just make, because there's an extra calcium, we have to show that a calcium ion, okay, is hanging out. So I'm going to put 1. Now, if there's 1 calcium ion hanging out, how many chloride ions extra should there be? For every 1 calcium, there's what? 2 chloride ions. So right, if you said there should be 2 more chloride ions. And that's how I work this drawing. So there should be more chloride ions than potassium ions, because there is excess chloride ions that were added. All right, so that's how that works. And I add a little bit of calcium because there was excess calcium. Not all of it was used up, so some of it's in the solution. And if that is my correct drawing there. All right, So that represents the end of this worksheet. Hopefully that helped.